Hi, welcome back. Hope you're doing well. Today we're going to continue talking about orthogonality, and we're going to talk about orthogonal complements today. Okay, so just a little reminder. Uh, we defined the dot product between two vectors in Rn that gives us a notion of length, because we take the norm of vectors by taking the square root of the dot product of a vector with itself. It also gave us some sort of notion of angles. And we said that two vectors are orthogonal if their dot product is zero. Okay, and that corresponds in Rn to really being perpendicular. Okay, and then we talked about how you show that two vectors are orthogonal, and also how you show that two subspaces are orthogonal. Right? So two subspaces are orthogonal if every vector in one subspace is orthogonal to every vector in the other subspace. Okay, so today we're going to talk about a specific situation related to this phenomenon. And here's what I'll say. Suppose that V and W are subspaces of Rn. Rn, so they both live inside the same vector space. Then if V is orthogonal to W, and the dimension of V plus the dimension of W equals n, then we say that V and W are complementary subspaces. Okay, so there are two subspaces that are orthogonal to one another, and their dimensions sum up to the entire dimension of the space. Okay, and the first two examples that we saw last time were actually examples of orthogonal or complementary orthogonal subspaces. Right, so the x-axis and the y-axis in R2, those are complementary because each of them is dimension 1, so the dimensions sum to 2, and we check that they're orthogonal. And then the second example, where we had the xy plane and the z-axis, again, we check that those are orthogonal subspaces. One of them is dimension 1, one of them is dimension 2, so their dimensions sum to 3, so those are also complementary. Okay, and even in this example, which we didn't go through, but I said that you can check yourself, we had two orthogonal subspaces, and they each had dimension 2, and they lived inside of R4, so those were also orthogonal. Those were also complementary orthogonal subspaces. Okay, of course, just because you're orthogonal doesn't mean you need to be complementary, right? A very easy example is in R3, if you take V to be the span of, just take the x-axis in R3, and take W to be the y-axis, then we've essentially already shown that these two things are orthogonal to one another. So then V is orthogonal to W, but they are not complementary. Okay, so somehow being complementary kind of means that they're as big as possible. Kind of means that they fill up the entire space in some sense. Okay, so let me now define the orthogonal complement of any subspace. And the orthogonal complement will be a complementary orthogonal subspace. Okay, so here's the definition. So let V be any subspace of Rn. Okay, then the orthogonal complement of V denoted V perp, so it's got a superscript perp on it, is the subspace consisting of all vectors which are orthogonal to V. Okay, so the orthogonal complement is you look at every single vector that's orthogonal to V. Another way to say this is that V perp consists of all of the vectors y in Rn such that x transpose y equals 0 for every x in V. It's all the vectors that are orthogonal to every vector in V. Okay, so you should check that V perp is a subspace. In other words, you should check that the 0 vector is in there. You should check that if you have two vectors that are orthogonal to v, then the sum is orthogonal to v. And if you have a vector that's orthogonal to v, and any scalar multiple is also orthogonal to v. This is standard, so you should check it. 0 is in v, sorry, v perp. If x and y are in v perp, then x plus y is in v perp. And if x is in v perp and c is a real number, then c times x is in v perp. Okay. And it turns out that the orthogonal complement will be a complementary subspace. So sort of the way that you get a complementary subspace is you take as many orthogonal vectors as you can. Right? So the reason why in this first example, these things weren't complementary is because, well, if you start with just v, say just the x-axis, then there's a lot more vectors that are orthogonal to v than just the y-axis. It's actually the entire yz plane that's orthogonal to v. But if you take all of those, then you'll get a complementary subspace. Okay, so let's develop some properties of orthogonal complements. Here's the first one. Okay, so let V be a subspace. Then one thing is that if you look at all the vectors that are in both V and its complement, all you get is just the 0 vector. Okay, again, this should be, I mean, we sort of saw this in all of the examples so far. Right, the z-axis and the xy plane, they only intersect at the origin. Same thing with the x-axis and the y-axis, those only intersect at the origin. In fact, this is true even if you just take an orthogonal subspace. You don't actually need to take the orthogonal complement. So you could replace this with any orthogonal subspace. Of course, because any orthogonal subspace will sit inside of V perp. Right? V perp consists of every orthogonal vector. So an orthogonal subspace will sit inside of V perp. And so if you make that thing smaller, you of course only make the intersection possibly smaller. Okay, and the proof is very simple. Suppose that x is in both V and V perp. Right, so if x is in V intersect V perp, that means that x is orthogonal to itself because it's in both V and V perp, right? Then x is orthogonal to itself. Right, in other words, x is perpendicular. I mean, x is orthogonal to x. This implies that if you take the dot product of x with itself, you get 0. But this means that the length of x is 0. But the only vector with length 0 is the 0 vector. So the only vector in the intersection is the 0 vector. And again, I wasn't using the full power that it was V perp. All I was using was that x was orthogonal to itself. Okay, so we've seen some examples of orthogonal complements already. There's also, by the way, there's a nice picture in the notes just to show you what's actually happening. The orthogonal complements are the biggest possible thing, right? So if you take this to be your subspace, that's horrible. If you take your subspace to be the z-axis, then this red subspace is the orthogonal complement, right? So if this is V, then this is V perp. That's all the vectors that are orthogonal to V. But if you take, just say, like a line in this plane, then this is just unorthogonal subspace. Well, this is the orthogonal complement, right? It's sort of the biggest orthogonal thing. Okay. Now, we also saw last time some like natural examples of orthogonal subspaces. In particular, we showed, that the row space is orthogonal to the null space. But you could ask now, well, what is the orthogonal complement of the row space? Right? Because we know that the null space is orthogonal, but it might not be every orthogonal vector. Right? But it turns out that it is. So actually the row space and the null space are orthogonal complements. They are orthogonal to one another, and in fact the null space is sort of every vector that's orthogonal to the row space. So let's state that as a theorem. That's a useful thing to know. Whoops. Okay, so let A be an n by n matrix. Sorry, m by n matrix, and not requiring square here. This is true for any matrix. Then the orthogonal complement of the row space is the null space, and the orthogonal complement of the column space is the null space of the transpose. Okay, so notice that this is a stronger result than what we proved last time, right? So let me just write what we proved down last time. Let me write down what we proved last time. Last time we just proved that they are orthogonal to one another. Today we're going to show that they are actually orthogonal complements, right? So this says that the null space consists of every vector that's orthogonal to the row space. Okay, so let's just prove the first one. The second one technically follows if you just take the transpose. Okay, so we showed already that they're orthogonal. Right, that means that we showed that every vector in the null space of A is orthogonal to every vector in the row space of A. So this means that certainly the null space of A sits inside of the orthogonal complement. Sorry. Right, the orthogonal complement is every vector that's orthogonal. The null space is at least some vectors that are orthogonal to the row space of A. We just need to show the opposite inclusion, right? To show that two sets are equal, you can show that each of them is a subset of the other, right? So we need to show that the row space, the orthogonal complement of the row space is a subset of the null space. How do you do that? Well, think back to the logic primer. You show that if you have a vector in the orthogonal complement, then you show that it has to be in the null space. So suppose that Z is in the orthogonal complement of the row space. I need to show that Z is in the null space. Okay, now we have to think about what happens when you multiply A by Z. Do you get 0? And the answer is, that seems like it's going to be yes, because when you multiply A by Z, what you're doing is you're taking the dot product of the rows of A with Z. And you're going to get 0 every time because the rows of A are in the row space. Right? And Z is orthogonal to every vector in the row space. So what's happening here means that we should write down A in terms of its rows. Right? So suppose that A is B1 transpose, B2 transpose, Bn transpose. It's an m by n matrix, so actually there's m rows, Bm transpose. Right? Or maybe I should say write A like this, because let's just write A in terms of its rows. Then clearly each Bi transpose is in the row space of A by definition. Right? The row space is defined to be this span of the rows. Each of those is going to be actually, if you take the span of the rows, certainly each row is going to be in the span of the rows. Okay, but then, since Z is in the orthogonal complement of the row space, this means that Z is orthogonal to every single row. So Bi transpose Z equals 0 for all I. Z is orthogonal to every vector in the row space, in particular, all of the BI transposes. Right, but then, if you take A times Z is, it's this multiplication. But the way that you get this multiplication is you just multiply each of these rows by Z, and you put them in a vector. Right? And each of these now is 0, 0, 0, which is just the 0 vector. This means that A times Z is 0, which means exactly that Z is in the null space. Okay. What I'll do before I print this out is I'll shift the whole thing up, so hopefully it doesn't go onto a second page. Okay, so this shows that we have a source of orthogonally complementary subspaces. You take any matrix, you can take its row space and its null space, and those will be orthogonal subspaces that are complementary. Okay, but it turns out that in some sense, this is all of the examples for orthogonal complements. In other words, if you have any pair of subspaces, V and W, that are orthogonal complements of one another, then you can write them as the row space and the null space of some matrix. Okay, and actually, it's not anything sort of fancy. Let me state this theorem. So it's just this: any subspace V in Rn is the row space of some matrix. Some m by n matrix. Hence, the orthogonal complement of V is the orthogonal complement of the row space of A, so it's just the null space of A. What this means is that you can write down all of the orthogonal complementary subspaces as the row space and the null space of some matrix. Right. Hence, any pair of subspaces V perp can be written row space of A, null space of A for some matrix A. Right, and the proof is just, well, V has a basis, right? And so you can just make that basis the rows of a matrix, right? So any vector space has a basis. This is, I think, proved in 308, right? So suppose that V is the span of some vectors. And I'm going to write them as row vectors because I want them to be, it's actually m, right? There's m of them. This doesn't have to be a basis, but we might as well take a basis. I could also say any vector space has a spanning set. Okay, then set A to be just the matrix whose rows are exactly these vectors. Then this implies that the row space of A is V. And then we just proved that V perp is the null space of A. Right, so anytime, I mean, this just shows that the example in the previous theorem, or the statement of the previous theorem, really actually covers all possible orthogonal complements in some sense. And it's just for the simple reason that if you have a vector space, a vector subspace, you can just make those the rows of a matrix, and that vector space is now just the row space of that matrix. Okay, but one thing that I sort of swept under the rug here is I've defined the word complement kind of twice, right? So at first I said that you call two subspaces complementary if their dimension sums to the entire vector space and they were orthogonal. But then I defined the orthogonal complement as all of the vectors that are orthogonal to the vector space. So this definition, I made no mention of the dimensions of the vector spaces. So in other words, I defined the word complementary and I defined the word orthogonal complement, but it's not at all obvious that the orthogonal complement is complementary to V. Right? By definition, the orthogonal complement is only obviously orthogonal to V. But I said that you would call them complementary if their dimensions summed up to n, and I never showed that's true for the orthogonal complement. Of course it is true, because otherwise I wouldn't have used the word complementary for this phenomenon, but it's something that we actually need to show. Okay, so we should show it. So here's the proposition. Here's the proposition. If V is a subspace of Rn, then the dimension of V plus the dimension of V perp is actually equal to n. In other words, every vector space is every orthogonal complement is complementary to the subspace, right? If you take all of the vectors that are that are orthogonal to V, and you sum up the dimensions, you will get the dimension of the entire vector space. Okay, and this follows from the rank nullity theorem in 308. Right, so we just argued, we saw that if V is a subspace, then there exists an m by n matrix A such that V is equal to the row space of A. I should say a subspace of Rn. Right? And we saw that V perp is equal to the null space of A. But by Math 308, the dimension of V, which is the dimension of the row space of A, is also equal to the dimension of the column space of A. Those are both equal to the number of pivots in the reduced in the echelon form of the matrix A. And by the rank nullity theorem, the dimension of the column space of A plus the dimension of the null space of A is equal to n. So now, well, this quantity is just this quantity, which is this quantity. And this quantity is just the dimension of, let me write this here, dimension of V perp equals dimension of the null space of A. Just so I have something to highlight. This quantity is this quantity, which is this quantity, right? Hence, the dimension of V plus the dimension of its orthogonal complement is equal to n. Okay, so what have we just seen? If you take any subspace you want, and you take that its orthogonal complement, then the dimensions sum up to the dimension of the whole vector space. We also saw a little bit ago that they intersect only at the origin. So what you have is you have sort of two big subspaces that intersect trivially. So turns out that basically these two subspaces, a subspace and its orthogonal complement, sort of fill up the entire vector space because their dimensions sum to the dimension of the entire vector space, and they intersect only trivially at the origin, which must mean that they sort of spread out in all the directions of the vector space. That's putting it sort of just illustratively. Let me state it really technically, which is that, in fact, you can get a basis for Rn by taking a basis of the vector space, of the subspace, along with a basis of the orthogonal complement and just sticking them together. That's sort of what I meant when I said the two subspaces sort of fill up the whole space. If you just union their bases together, you get a basis for all of Rn. So that's a very useful thing. This allows us a way to sort of decompose all of Rn into two smaller spaces. And maybe I'm only interested in some subspace of Rn. And there will be applications very shortly where we'll see that you're interested in some specific subspace of Rn. It's very nice to be able to write every vector in terms of a basis of that subspace, plus in terms of a basis of the orthogonal complement, the rest of the vector space. Okay, so if V is a subspace of Rn with basis, let's call it BV, and say it's A1 through AR, so it's an R-dimensional subspace, and V perp has basis, let's call it BV perp, and it's called A1 prime, and we know how many vectors there are here because the dimensions need to sum to n, so there must be n minus r vectors in this basis. Then if I take the union of these two things and call it B, this is just, I take all the vectors in the basis for V, and I append all of the vectors in the basis for V perp is a basis for Rn. And like I said, this will come in legitimately extremely useful when we're interested in a certain subspace. We can take any vector and sort of write it in terms of the subspace and in terms of something in the orthogonal complement. And we'll be able to see this geometrically. So this seems like a really technical point, but it's actually very useful and very geometric. Okay, and let me not formally prove this. There is a proof in the notes, but I actually don't think the proof in the notes is totally complete. And I think in order to really prove this well, you need to develop a little bit more technical machinery than I want to in this course. But let me just sort of, in broad strokes, explain why. It's basically because the dimensions of V and V perp sum to n, and they intersect in as small a place as possible. That's really the reason why. In other words, they sort of don't overlap at all. And so if you take a basis for one and a basis for the other, because the two vector spaces intersect only in the zero vector, as you add the basis vectors from BV perp, you're going to remain linearly independent as you go. Okay, so I mean, you can certainly read what's written in the notes. What's written in the notes nothing there is incorrect. I just think it doesn't quite show that if you take the union of the bases, you actually get a basis for Rn. I think all it shows is that you could add any individual vector. Like you could add any one of the primed A's to the set BV and end up being linearly independent, which is true. But it's not quite enough because then you want to add the next prime vector, and I don't think what's in the notes is actually quite good enough. Regardless, it would have been a technical proof anyway. Even the thing written in the notes is pretty technical. It's not so important to know the proof, but it is important to have a geometric idea of what's happening. Okay, so actually the corollary, or the proposition directly after this one, is really the important thing anyway. Okay, so let me state that one. So maybe let V be a subspace of Rn first of all. Okay, then every vector B in Rn can be written, of course, as a linear combination of this basis. Right, so I'm really extending the previous proposition. It can be written B is equal to C1 A1 prime up through CR AR prime plus C1 prime A1 prime plus Cn minus R prime A n minus R prime, right? In other words, you can write every vector in Rn as a linear combination of these basis elements. But then what you can do is you can notice that this thing is in V, right? Because it's a linear combination of the elements in V. And then this thing is in V perp because it's a linear combination of elements in V perp. So you can write every vector in Rn as a vector BV plus a vector BV perp, where BV is in V and BV perp is in V perp. That's the real reason why we want the previous proposition. You can take any vector in Rn and write it as something in V plus something in V perp. Okay, so what's the picture? The picture is the important thing here, right? So the picture is, suppose, let's just take our favorite vector space V, which is the xy axis, but this will work for any subspace. If you take any vector that you want in Rn, what this proposition says is you can write it as something in V plus something in V perp. Well, you can, right? So if I drop this line down here to a right angle to my vector space, then I can write this vector is BV, and this vector is BV perp. And you'll notice that BV perp is, in fact, inside the orthogonal complement. This thing is V perp. So you can see how this is going to be sort of geometrically useful. Well, maybe you can't see it yet, but you can at least hopefully see why you should believe the previous theorem. How do you write a vector as something in V plus something in V perp? That's really the subject of our next lecture, which is going to be on projections. So this vector BV is going to be the projection of B onto V in actuality. This is going to be the projection of B onto V. And it turns out that what's left over is going to be orthogonal to V. And just from a geometric standpoint, what you're doing is you're just getting the closest vector in V to B. Right? You take this vector V, B, you look at the subspace V, and you take the closest vector that you can. It's closest in the sense that it will be a right angle away. Okay, note that there's a good warning in the notes, which is that what this theorem is not saying is that every vector is either in V or it's in V perp. Right? So when I said something like, oh, well, V and V perp sort of fill up the entire space, I'm not saying that every vector in Rn is either in V or it's in V perp. What I am saying is that every vector can be written as a sum of something in V and something in V perp. And actually, since these things were a basis, there must be a unique way to do this, right? Because the expression that you have here for B, the scalars are unique because the A's and the A primes form a basis of Rn. Okay, and since I have a little bit of time left over, I want to talk about one of the problems from your previous problem set 2. It was number 3. This was the red dagger problem. And I left a little footnote that says that these red dagger problems are going to be related to projections. Okay, so let me write this here on this page. Problem 3 was about if you have a linear transformation from Rn to Rm such that a squared equals a, right? That was the setup. And how is this related? Okay, and this will become clear both next lecture and in the coming lectures. What you can consider is the linear transformation. Okay, what I say is fix a vector space and fix a vector subspace V. So you could imagine like this red plane in this picture as our fixed vector space V. And for every vector B in Rn, we'll map it to this BV that I've drawn in the picture. Okay. What we're doing is we'll project it down onto the subspace. Now, in the next lecture, we'll get into more detail about this, like how to actually write down what the projection is. But if you think about that linear transformation, well, if you do it twice, if you project B down to BV, and then you project BV down to V, it'll just spit out BV again. So if we map every b to the closest point on the vector subspace, that actually ends up being a linear transformation. That'll be a projection, and it will satisfy exactly this a squared equals a, because if you do it twice, it's the same thing as doing it once. Okay, and so you'll have a sequence of problems throughout the course that will develop more and more ideas of projection, but we can already understand it. I mean, even last week when you were doing the problem set. Okay, so might as well go over this problem. It's related to projection, and we'll see. So again, we had a linear transformation Rn to Rn such that a squared equaled a. And the first thing that you had to do was you had to argue that lambda equals 1 is an eigenvalue, and that it has eigenspace, which is the column space of A. Okay, and here's the point. The point is, if x is any vector in Rn, then if you look at a squared times x, since a squared is a, that's the same thing as a times x. Right, so what do you have? This means that you have a times ax equals ax. This means that ax is an eigenvalue, as an eigenvector with eigenvalue 1. So ax is an eigenvector with eigenvalue 1. And this works for every single vector x in Rn. So what kind of vectors can you get as eigenvectors? It's you take any vector x in Rn, you multiply by a, that'll be an eigenvector. But if you take a look at all the vectors that look like ax, where x is in Rn, this is another definition. In fact, it's the definition we gave of the column space of A. Okay, so what does that show? That shows that every vector in the column space of A, every possible ax, is an eigenvalue with eigenvector 1. So what that shows is that the column space lives inside of the 1 eigenspace. But we still need to show the opposite inclusion. And the opposite inclusion takes just a little extra thought. So suppose that y is in the E1 eigenspace. What does that mean? That means that ay is equal to y. Right, but now look, that already shows that y is in the column space because y is equal to a times something. So this shows that y is in the column space, which gives us that E1 is a subset of the column space. Okay, so really nothing too tricky in this problem. It's just about using the correct ideas in the correct order. Okay, and notice that it agrees with whatever intuition we should get from this picture. Because clearly, under this projection transformation, which again we'll learn more about next time, there's a whole bunch of vectors that are fixed, which is everything in the red plane. Everything in V is fixed by projection. And also that's exactly the same thing as the range of the linear transformation, the column space. The red plane is, you can think of the red plane also as all the vectors that you could possibly get by projecting. Okay, so this, hopefully you're seeing that this problem is related to this picture. And again, we'll develop that idea more throughout the quarter. What was part 2? Part 2 was, right, what happens if A is invertible? Right? So, part B rather. If A is invertible, then the point is, okay, here's the big hint in this class. If you ever see invertible or not invertible, you should look at the big theorem to see what that means. If A is invertible, then by the big theorem, or by the unifying theorem, or by the invertible matrix theorem, this means that the column space of A is equal to all of Rn. And we just saw in part A that the column space of A is the 1 eigenspace, assuming that A squared equals A. So what is this? This is every single vector in Rn is an eigenvector with eigenvalue 1. Which means that every single vector is fixed by A, right? So this means that AX equals X for every X in Rn, which means that A is the identity matrix. Another way to see this is because this means that A is definitely diagonalizable because it has n linearly independent eigenvectors. What are the n linearly independent eigenvectors? You can just take the standard basis, right? So the eigenvectors, or a basis of the eigenspace, is just E1, E2, up through En, and the eigenvalues are all 1, 1, 1, 1, 1. So if you were to write down the diagonalization of this matrix, it's the, I mean, it's just the identity matrix 3 times is the whole point. Okay, so the only invertible matrix that satisfies A squared equals A is the identity matrix, but it follows from part A. Okay, what about part C, which was, what can you say? I think it was, what can you say if A is not invertible? Right, well, again, we know that the one eigenspace is the column space of A, right? So E1 equals the column space of A. So this one has dimension which is equal to the rank of A. Right? The rank is the dimension of the column space, or the number of pivots. Those are the same thing. And then you have sort of by the rank nullity theorem, you should have the remainder of the columns will correspond to a basis of the null space, right? So by the rank nullity theorem, the dimension of the null space of A, that's the nullity of A, is equal to n minus the rank of A. But an important point is that the null space is an eigenspace. The null space is exactly the eigenspace with eigenvalue 0. All right, it's all the vectors such that AX equals 0x. So the null space is equal to the E0 eigenspace. But now we have enough vectors, right? We have m vectors in the column space, that's E1, and then we have n minus m vectors in the null space, that's E0. And so we already have a basis of eigenvectors. This must mean that we have all of the eigenvectors. Right, so if this thing has rank R, then this is n minus R. So we have n linearly independent eigenvectors. You just take a basis given by a basis of column space, which is, again, the E1 eigenspace, and a basis of the null space, which is the E0 eigenspace, which means that we must have found all of the eigenvectors, which means that we must have all of the eigenvalues. Right? The only possible eigenvalues are 1 and 0. And that also agrees with this picture, right? If you think about what vectors can possibly be scaled by this transformation, basically the plane is fixed, right? That's the E1 eigenspace, and everything perpendicular, everything orthogonal to the plane, in other words, the orthogonal complement, when you project down, will get smashed into the origin. So those things are all scaled by 0, and the plane is scaled by 1. And they're orthogonal complements, so they sort of have enough, you have enough linearly independent vectors in V and in V perp that accounts for all of the eigenspaces of A. Okay, so this problem 3, we of course we didn't define projection before you did that problem, but all these properties follow just from the fact that a squared equals a. And a projection will also have that property. If you do it twice, it's the same thing as doing it once, right? So just because when you do it twice, it's the same thing as doing it once, you actually already know all about the eigenvectors and eigenvalues of a projection. And this should agree with our geometric picture here. Okay, so it's going to be a really important concept. We'll see that in the next lecture and the lecture after that. And I hope that by the end of these lectures, you have a really good picture in your head of what projection is, how projection works, and then in the applications, you can have like a good high bird's eye view of what's actually happening in the applications. Okay, I think now I'm out of time, but if I have time in lecture throughout the course, I will try to shed a little bit more light on the problem set problems that you've already turned in. Right? Of course, in quiz section, you talk about problem set problems that you have already or you have yet to turn in, and I'll discuss with Sam. I'll ask him sort of what he's covered in those things, because the problem set problems are such a core component of the class. All right, see you next time.